Okay, hi guys. So, in this lecture, I'll be talking about the optical purity or enantiomeric access. And before that, let us see the DL and DL configuration in case of amino acids. Okay, so if you have an amino acid, so the general formula of the general format or pattern of amino acid is something like this. We have NH2 here, CO2, H here, and R here. So what happens is um, and obviously this would be the carbon across which the D or L configuration would be decided. So the hydrogen atom actually detaches from the CO2 to form a CO2 minus, and N actually takes that hydrogen atom to form NH plus. Okay, so this is a D amino acid. So this is the first priority, this is the first, this is the second, this is the third priority, and it would be clockwise again because of the horizontally placed H atom. So it would be D amino acid. So this acid is also known as one zwitran or dipolar salt or inner salt because of the charges separated within the compound. Okay, it is called inner salt and dipolar salt and zwitran. Okay, so let's take an example to find the D and L configuration of another amino acid before moving into optical purity of compounds. We have something like this. So what would be the configuration for this? Obviously the configuration would be decided upon this carbon atom. So this is the first priority, this is the second priority, this is the third priority. Configuration would be D amino acid. Okay, so now let's move on to optical purity or enantiomeric access. Okay, next topic is optical purity. Optical purity, it is also known as enantiomeric access. Enantiomeric access. Okay, so let's say we have a mixture in which we have 4 gram dextrorotatory compound and 6 gram levorotatory compound. Okay, so what would be the optical purity for this? Optical purity for this would be 20% because, and 80% would be recipe mixture. Recipe mixture would be 80% because if you just see I hope you remember what is a racemic mixture. Racemic mixture is equimolar concentration of D and L or R or S um, in a mixture, right? So equimolar part of D L in case of amino acids and carbohydrates, and RS in case of others. Okay, so if you just look closely on this example, the 4 gram part till here would be racemic, and the remaining 2 gram would be available for optical purity. Okay, so a total of 2 gram out of 10 gram total D plus L times 100 gives me 20% purity. Okay, similarly let's take another example in which we have 4 gram L and 6 gram D. So what would be the optical purity? It remains the same whether it rotates the PPL or plane polarized light in right direction or left direction or in anti-clockwise direction or in anti-clockwise direction. It does not matter. We are talking about the general optical purity. Let's say we have L and D 5 gram and 5 gram. Okay, so what is the optical purity in this case? 0%, because they are the mixture is external compensating themselves or itself. what would be the optical purity for I hope you have now gotten a fair amount of idea as to how do we calculate the optical purity. So without wasting any more time, I'm just writing the directly I'm writing the formula for calculating the optical purity. So optical purity, you can write that formula: D minus L, the concentration of D minus L, the mod form, and D plus L times 100. This would be the formula for optical purity. Okay. So it can also be termed as observed specific rotation, observed specific rotation divided by a specific rotation of enantiomer or pair enantiomer. A specific rotation of enantiomers, okay, times 100. Okay, so I'll just draw a table and we'll just do some examples or some quick exercise on it. So we have I have given you the concentration of D, L. You need to determine the optical purity and the racemic mixture percentage. Okay, so we have D as 100 gram, L as 0, optical purity is 100%, racemic mixture is 0. D as 70, L as 30, optical purity would be 40, racemic would be 60. 50-50, 0 and 100. Okay, if we have 30-70, again 40 and 60. If we have 10 or 90 maybe, then 80 and 20. And if we have 0 and 100, 100 and 0. Okay. Okay, so this completes our part on optical purity. Now let's quickly come on to our next topic, which is called resolution. Okay. Now let me write down the heading. Resolution. So by resolution I mean the separation of enantiomer pair method is known as resolution. So separation of enantiomeric mixture is known as resolution. Okay, so we can say whether the mixture is resolvable or non-resolvable. Okay, so for this let us take some examples. If we have D and L in a mixture, and if we supply it with D, then we can have some DD diastereomers and DL diastereomers. Okay, we will have diastereomer, hence the mixture is separated. So this is optically pure and this is racemic. Okay, similarly if we have something like D and L as racemic, we supply it with L, then also it will form a diastereomer of LD and LL. Okay, so hence if a compound is racemic, then obviously it can be separated by providing it with the optically pure substance, and it will convert it into diastereomers. Okay, so now let us take some examples on determining whether a given compound is dissolvable or not. We have, so is this a chiral compound? Yes, it would be optically active, it would have enantiomers, so it is resolvable. Let us take second example. Here we have so is this the compound is this compound a chiral? No, because it is having a POS, but still it is having a chiral center, hence it is a meso compound, hence it is non-resolvable. But because it is not showing any optical purity or optical activeness, so it is also non-resolvable. It is not a chiral center, it will not show optical activity. So we have something like this. So in case of biphenyl, we already studied the stereochemistry of biphenyl. I hope you remember. If you don't, just go back to the lectures and revise and revise. This is the only funda of cracking high scores in organic chemistry in any of the J level examinations or any other competitive examination, is that you revise, you re-revise, you again do the questions, you make your concept strong, things like that. So this is the stereochemistry of biphenyl. This would be at 90-degree ring, so it would be resolvable because it will show optical purity. There is a stereogenic area, which is this one. Okay, if we see at this compound, it is having a chiral center, but we also took the stereochemistry of amine inversion or amines. In this case, we found out that it will not show optical purity or optical activity, hence it would be non-resolvable because of amine inversion. Reason is amine inversion. Okay, so to summarize, I can write that if we have a optically active compound, then it is resolvable. If we have optically inactive compound, then it is non-resolvable. And if we have again amine inversion, then again it would be non-resolvable. Okay, so with this we come to the end of this lecture, and in the next lecture we'll be seeing some of the applications of isomerism. So till then, good luck and goodbye.